start off with. So what we're looking at today is going to be what's known as the that fun sequence of titles. Okay? 90% of the labs that we're doing in 152 are all titration labs. So you're going to be pulling out the burettes and measuring things really carefully with the burettes, looking for color changes, that kind of stuff, which I think you did for one experiment in 151, right? So you're going to get really, really used to titrating things, right? So for today's lab, they've got the introduction kind of organized into pseudo sections that we would kind of expect, or that would kind of work for your introduction. Okay? To start off with, it's usually a good idea. Sorry, that's getting settled. What are you guys doing for the lab report for this one? It's the introduction and the results and conclusions? Okay, so let's be careful with the introduction. Your goal of the introduction is to try and introduce the main topics and kind of the main idea on why you're doing an individual experiment. Okay? So we've got a bunch of different sections organized in here, and one of the first things that you want to do when you write your introduction is get to the point first. Why did you do this individual experiment? So if we take a look at the introduction given to you, what would you think is why you're doing this experiment? What's it start off with? Complex ions. So you might run under the assumption that what we're studying is complex ions. Is that really what we're studying? No. What are we looking at in this experiment? We're looking for water hardness. Okay? So the first thing that you would probably address in your introduction is not so much the complex ions, but what's going on with the hardness of water. Okay? Why is that something important to evaluate? Okay? Why should we look at the hardness of water? What problems does it cause? Okay? So that's ultimately your second section of what they've given to you. Okay? The next part of it is then going to start to address kind of the complexities of the hardness of water. Okay? So I think they've got it in here. There we go. To have hard water, what we're looking at is in that second line. Okay? We're looking at all of these metal ions contributing to hardness of water. Okay? So if we're going to come up with an experiment to kind of monitor the hardness of water, we would have to be able to account for all of those ions. Okay? Well, based on your reading, does our experiment actually monitor all of those ions? No. Okay? So why did we change the experiment? Okay? Why do we not monitor every single one of those ions? What ion are we monitoring? We're only evaluating calcium. Why do we only focus on calcium? When we're looking at hard water, it's the one that contributes the most to hard water. Okay, so it's going to be our largest contributor. That's the one we want to zero in and focus our discussion on is calcium ions. Okay? Which adds kind of an extra issue along with this. If we take a standard sample, just tap water, and try and test its water hardness, we've got a lot of other ions floating around in there. And depending on our experiment, what would those ions potentially do? Change the results. Okay? So as kind of a limitation or one way to simplify your experiment, what we're going to do is give you a standardized hard water sample where the only ion that you're calculating or looking for is for the calcium ion. Okay? So that's to kind of help with your experiment. Okay? We could then push this a little bit further and say, okay, calcium is the most important. How would we report whether or not the water was hard or not? Okay? Because we can't go up to water and just hit it and say, oh yeah, that feels hard. Okay? That doesn't exactly work. What do we have to do? Come up with some way to monitor the calcium ion concentration. So we could report it in a concentration. Molarity. That's our standard unit when we're chemists. Unfortunately, what unit do we actually use in this case? Milligrams per liter. Okay? So we're now using a new unit, a non-standard unit as far as we're concerned. That unit should get mentioned in the introduction because we're now changing our standard focus. Okay? Why do we use that unit? Okay, we can read a little bit further back in our statement. What does it say? Unfortunately, you get a lot of this kind of stuff. By convention, we just decided it. Okay? What was that convention from? It was probably a series of non-scientist people testing water hardness, and the easiest way for them to measure water hardness was something that they could actually weigh out and get a numerical value for, hence a mass and a volume. Okay? Molarity, while it may be useful for us to use in the chemistry world, we can't measure moles easily. Okay? Even when we get into the lab, we measure grams and then convert to moles for our balanced equations. So it just came from a necessity on what we were working with. Okay? When we're dealing with water hardness, we weren't concerned about a balanced reaction or any kind of reactions occurring. We just needed to know how much calcium was physically there. The mass works perfectly well for that. Okay? And because that's what they started with, somebody big and angry said that's what we're sticking with. Okay? So that's one of the reasons we see these units change. Okay? Make sense? So that's all fine and dandy, except is that the final unit that we're using? You all read it, right? No, it's not. What other unit do we look at? Parts per million. Why on earth would we shift the units again? Good question. I have no idea. Okay. It's again probably a convention thing. Someone went through and decided that that milligram and that liter thing was too confusing, and so they switched it up to a new unit and went to parts per million. Okay? Because it's easier to talk to someone and say 1 part per million than it is to say 1 milligram per liter. Okay? Particularly being Americans. We don't use grams very well, and we don't use liters very well. Okay? So when we shift to parts per million, that's kind of standard across the board. No matter what units you grew up with and worked with, parts per million is always going to hold true. Okay? So you're going to end up reporting your water hardness calculation results according to 2 things. Okay? The milligrams per liter and your parts per million. Okay? So we're going to have to be able to calculate all of those. And we'll look at some of the calculations as we go. Okay? So now we've got an idea on what to report, why we're doing it. What do we need to come up with now? Okay, what are you going to do when you go into lab? We could look at hazards, but that's pre-lab. I want to know about the experiment. Okay? You need to tell me how you get that calcium ion. We said why we want to know the calcium ion concentration. We said how we're going to report it. But how do we get that number? How do we get the milligrams and the liters? We could weigh out all the calcium carbonate, but it's dissolved in water. How do we get the calcium carbonate away from the water? That's a little bit more difficult. So what we'll do is move to another situation. We'll pick something else that will react with one of those species. Which one are we concerned about, the calcium or the carbonate? The calcium ion. Okay? Calcium ion happens to be a +2 charge. Okay? And as you'll start to learn when you move into organic chemistry, what would be attracted to a +2 charge? Anything remotely negative. Okay? So what we're going to try and do is pick some kind of extra species that can react with the calcium ion that's present. Okay? And we need it to react in 2 ways. Okay? One way, first off, what's the color on calcium? White or colorless, we aren't going to see it in our solution. Okay? So one thing we need to for sure do is somehow get something observable in there so we can see it. So our calcium ion needs to react with an indicator. Okay? So if a calcium ion is present, we would see one color versus another color. Okay? The other thing we need to do is get that calcium to shift from the solution out of the solution in a very measurable way. Okay? An indicator, unfortunately, tends to react very, very quickly. So as soon as you put a small amount of indicator into a solution, It very quickly changes color and gives us a result right away. Okay? We can't measure fractions of drops easily. Okay? So we have to come up with another method to monitor. That's where we move to the species of EDTA. Okay? So EDTA and, for that matter, the indicator, both coordinate to the metal. Okay? And it's referred to a coordination bond, not an actual bond, because we're looking at very loose sharing of electrons. Okay? So we can now move up to what's happening with our EDTA. Oh, that's right. Okay. Now we can go back to EDTA and what's happening with that. Okay. And they titled this complex ions, but it's not super necessary to refer to it as a complex ion. The complex ion is ultimately trying to say is that we get that coordination. In this case, they put copper. That was nice of them to pick the ion that you're working with, right? So let's make that calcium. Okay. So if we added calcium ion to a solution, it's going to interact with other species that are negative. Okay. Why did we show these bonds out to nitrogens? Is NH3 negative? I know it's a bit of a stretch for you. Nope, it's neutral. Okay, why would it coordinate to the calcium? If you drew out the Lewis structure of NH3, I know that's a long time ago, right? What do you get in your Lewis structure? You get a lone pair of electrons. What charge are your electrons? Negative. Those electrons can weakly coordinate with the calcium ion to neutralize that positive charge. Okay, it makes it more stable. Okay, so it's that coordination that we're going to try and rely on. Okay, so our indicator, when we add it in there, will react with our calcium ion and change color. Okay, we now need to come up with something that we can add that's going to take the calcium away from the indicator. Yeah.
I still don't understand why the ammonia needs to be there.
We'll talk about exactly why the ammonia needs to be there at a later date.
Okay.
Later date. 5 minutes, 10 minutes.
Okay.
So we need something in there to take the metal ion away from the indicator so that the indicator can swap back to being colored, or a different color. Okay? So that's where we're going to add the species EDTA. Okay? EDTA, also known as ethylene diamine tetraacetic acid, okay, is referring to this compound down here. Okay? When you go through and look at this structure, you did a great job highlighting things that aren't supposed to be highlighted. Okay? This compound, first off, when we looked at the previous one, we said the nitrogen had lone pairs. What do we have on these nitrogens? Lone pairs. So these nitrogens can coordinate with a positive calcium ion, just like the nitrogens in our previous example. Okay? This species acts as a better reactor, if you will, with the calcium than the free nitrogens, okay, than the NH3s. Why would that be the case? Okay, in our previous case, we had the NH3s scattered all over the place, different molecules floating around. In this case, where are the nitrogens? They're on the same molecule. Okay? If we've only got one molecule with two binding sites, as we get the interaction in, our calcium ion, say, binds to one, but now what's right next to it? Another one. So it can really quickly bind. In the case of the NH3, we had 4 molecules. Or sorry, 5 technically molecules, if you will. You had your ion and 4 nitrogen molecules floating around. We would have to get a lot of those to all come together at a perfect instant to form that complex. Whereas here, as soon as we form one, we can form the next one very, very rapidly because it's extremely close. Okay? What we're looking at in just those nitrogens is something known as a chelating agent. Because what it does is it grabs a single molecule, will grab another single molecule in multiple ways. Okay? It can be referred to as bidentate or multidentate. Dentate being teeth. Okay? So it has multiple ways to grab a hold of or bite into another molecule or ion. Okay? EDTA is even more special beyond just those nitrogens. Okay? We also have, at the tail end, these acetic acid groups. Anybody know what kind of functional group those are? Just throwing it out there just to see. Carboxylic acid. What do acids do? What's that? Kind of, very particularly. How do they break apart? They donate hydrogen ion. What charge is a hydrogen ion? Positive. Which means if we remove that hydrogen, what charge does that oxygen become? Negative. What's special about that negative? What does it want to interact with? A positive. Where do we have a positive? Our metal ion. Okay? So not only do we have two positions from our nitrogens, which we've already seen, but we now have even stronger bonds coming from our oxygens. Okay? So EDTA will wrap and grab a hold of metal ions or positively charged ions extremely strongly because of all of these different ligands that could potentially donate electrons in and wrap around that individual ion. Okay? So it is an extremely common chelating agent. It's extremely strong because of that. Okay? So it's used in lots of different processes. They mentioned some medical purposes, which you have to be a little bit careful with. Okay? So one of the things that's interesting about chelating agents is they will grab a hold of individual metal ions, but what metal ion do they grab a hold of? Positive ones. What charge are your metal ions? You guys remember this? All metals are positive. So if we tried to intake EDTA to try and remove a metal ion from our body, great, that works. So there's a lot of common, typically elderly people that will ingest lots of EDTA to try and remove the toxic metals. That's fantastic. It does remove toxic metals. What else does it remove? The non-toxic metals, the ones that we need to survive, like iron. Okay? Why is iron important? It's what holds oxygen. Okay? So when you deal with chelating agents, you have to be very, very careful with what you're working with and why you're using them. Okay? So the more common useful techniques for EDTA are when you know that you've been exposed to a particular toxic metal. Okay? Beyond that, okay, it just kind of depends. Usually they're used as kind of snake oil. If you've heard of that, snake oil salesman. Right? Take this EDTA supplement, it'll cure you of all your ills and potentially kill you. But if you're dead, you can't sue me later. Okay? So kind of be aware of what individual drugs are trying to do. Okay? So it's kind of a neat tie. Okay? So our EDTA will bind to calcium. Because it's binding to the calcium in, was it 6 different ways, it's going to hold that calcium ion really, really, really tightly. Which means if we've got the indicator in solution, yes, it interacts with our calcium, but in theory, it doesn't interact very strongly. So that when I add EDTA into the solution, it takes the metal ion away from the indicator and keeps it. Now the indicator doesn't have the metal ion anymore, and its physical state can change. And that's what we end up watching for, is the indicator. Okay? So let's kind of scroll to those equations so we can get an idea of what's happening. Okay? So the first thing that we'll be looking at is our indicator, which they've kind of abbreviated here as H2IN, IN for indicator. Okay? When it's not bound to metal, so when we're in the reaction with it, it isn't there or hasn't reacted with it yet, that indicator is blue. Okay? When we run through the reaction where the metal reacts with it, it changes the color of our indicator because now the metal comes in, swaps out for our hydrogen ions, and we get a pink color. Okay? So when we start off our experiment, we're going to have some metal ions or calcium ions in the solution. We'll have some indicator in there. What color would we expect to see? Pink. Because pink is where we have the metal bound to the indicator. Okay? Once we now have our solution set up and ready to go, we now need to slowly add the EDTA. Okay? How can we slowly add EDTA? Happens to be a solid. I don't know if you guys looked that up. It's a white solid. Okay, so you all said dissolve it in water. Why did you dissolve it in water? Okay, it's dissolved in water. This is in water. Why not just add the solid directly to this? Comes to control. Okay? Control and time. If you want to add small amounts at a time, we could add a grain of EDTA each time. But every time you do that, what do you need to know about that grain? How much it weighed. So you'd weigh out a grain, go add it to your solution, swirl it around to get it dissolved. Nope, didn't change. Go weigh out another grain, add it in. That gets a bit tedious. Okay, so we want to come up with some way where we can standardize it and get that into an easy way to add. Okay? That's why we shift to a solution. Okay? What's the problem with using a solution now, though? What's the concentration? How much EDTA are you adding? Okay? When it was pure EDTA, you know it was just EDTA. Everything that went in there was just EDTA. Now when you add your solution, are you just adding EDTA? No, you're also adding water. So one of the issues we have to watch out for now is not just that we're adding EDTA, we're also adding water, and we're adding the EDTA in a varying concentration. How much EDTA do you know you're actually adding? How would you find that out? You would need to know the concentration of your solution. So one of the first things that you're going to do is make this EDTA solution, and then you have to standardize it. You need to know what the concentration is. Okay? And we'll look at that standardization as far as calculations go. Once we've got it standardized, as I slowly add the EDTA, it's slowly going to start to pull metal ions away from the indicator. As long as there's still metal present, the indicator is going to stay pink. So we keep adding EDTA until the metal gets pulled off. Okay? Now the indicator doesn't have any metal attached to it, and it now is in this state, and we see that blue color change. Okay? At that point, we know we've removed all of the metal that was in that solution. And we've trapped it all with the EDTA. How much EDTA is required to remove a single molecule of metal, or a single atom of metal? If I add one molecule of EDTA, how many atoms of metal will react with it? What did you say? One. How do you know it's one? That works too. There's another way to do it. What is this? And don't tell me a demonstrative pronoun. It's a balanced equation. The balanced equation allows us to see the metal and EDTA relationship. What's up?
Just wanted to make sure that you knew some of the mechanics of how we're doing it. It's not the same as it had been done before.
Oh, that's fun.
We're going to check out burettes and pipettes at the window.
Yep.
The unknowns are in individual bottles
Okay.
that I'll check out at the window.
Okay.
And the knowns will be pipetted from bottles in there.
Okay. Okay, that makes sense.
Okay.
Thanks. Might have been nice to know a little bit earlier, but oh, I'm recording. So what we're trying to do is look for that color change. Okay. So what you're going to end up doing is slowly adding the EDTA via the titration technique using your burettes. So the burettes you'll have to get from the stockroom. You'll have your EDTA solution, and you'll slowly titrate in until you see that color change. Okay? So just like you would have done with phenolphthalein, which I think is what you used as your last indicator. Okay? The indicator used in this case, because this is now also an important thing that we should talk about with the introduction, is Aerochrome Black T. Okay? It's a different indicator than you've used before, so you should include some information about it. Okay? It has a slightly different color change than you would expect, pink to blue in this case. Okay? Something in theory you knew before going into lab. And so you're going to be looking for that color change to determine when you've reached the endpoint, when the EDTA has completely removed all of the metal ion from the solution. Okay? One of the complications with this indicator is it's a little bit slower than phenolphthalein. Okay? So it takes a little bit more time to get that full color change. So as you add, you'll add slowly, do your constant swirling while doing it. Your first trial through, do a little bit faster than you would the others. And when you get close to within probably 5 mils of your endpoint, start adding it much, much slower, okay, and giving it a good little bit of time to mix evenly, okay, so that way you can get the appropriate endpoint without overshooting it too far, okay? Questions about any of that so far? Okay, someone brought up the ammonia issue. Ammonia acts as a weak base, okay, and in this case we're going to add ammonia and ammonium. Okay, ammonium acts as a weak acid. Those two are going to balance out the concentration of H+. Okay, so the H+ concentration stays relatively the same throughout the course of the reaction. Why do we care about the concentration of H+? Shows up in the reaction. Okay? If in the course of adding the EDTA, the H+ concentration changes, what happens to the indicator functioning properly? It doesn't. Okay? So what we have to do is add some secondary solution to that to balance out the concentration of H+, so it doesn't change in the course of the reaction, so that our indicator functions properly. Okay? Sound good? Okay. Whoops. Yeah, gotta go over here. So your procedure, you're going to start off with standardizing the EDTA solution. You want, for the experiment to work appropriately, you want a molarity that's about 0.004 molar. I don't remember, so they do tell you. You will use about 500 milliliters of solution just to kind of cover all your bases. You'll measure out roughly that mass of EDTA, and you'll dissolve it in your 500 milliliters. Once that's dissolved, you now have an approximate idea of the molarity. You need a super accurate one. Okay? So what you'll do then is do a standardization. In that standardization, what we're going to do is test the concentration of EDTA against a known concentration of calcium ion, because that's what it's ultimately reacting with. Okay? That known concentration is supplied in the stock, or I think in our room, I think is what he was saying. So we'll have that available. You will then measure out that known amount. So that's our standard calcium stock solution. We'll put it into our Erlenmeyer flasks so they're easier to work with. We can add a stir bar to help stir it. So this actually makes your life easier. You don't have to hand swirl. You can use the stir bars to do that for you. And then we're also going to go through and add the other things that are necessary to this. For instance, your ammonium chloride. For some reason I thought there was something else. Water, just to kind of dilute, just for the sake of it, I guess. And then the ammonium chloride. Ammonia is actually toxic, so watch out for that. Be aware of it. The toxicity level is like 1,000 times higher than what you can smell. So if you're smelling it, it just means you shouldn't continue to smell it. Okay? And you should be fine. Okay? It is found in all sorts of cleaners and stuff like that, so it's not that big of a deal. Just be aware that you shouldn't be huffing it, because it's not a good thing to do. Okay? What you're going to record. So let's, if I can do this. So what do we have for our standardization? So when we go through our standardization, sorry, that was a bit sloppy. We're looking at, again, our EDTA reacting with metal ions to give us our metal EDTA complex. Why did I remove the indicator from this? Is the indicator directly interacting with either of those? No. Okay. The indicator's there only to test for the presence of metal ion. Okay. What does the indicator tell us, though? Okay, what's that? Yes. What happens when the indicator changes color? It tells us that the concentration, or sorry, not the concentration, the moles of our metal ion is equal to the moles of our EDTA. So if we know one of what those mole values are, we can then calculate what the other one is. Okay? So our standardization, we're going to start with, I don't want to close out of this. Does it tell you what the concentration of calcium ion is in our standard?
Yes.
I know it's on our bottles. I don't know if it's in your procedure. Someone have it? So we know our concentration of our metal ion, 1 gram per liter. Okay. And that's of our metal. We'll go ahead and say calcium ion. Okay. Our balanced equation tells us the mole-mole ratio. Okay. So let's go through and figure out. Let's assume we've reached the end point, and we're going to try and figure out the moles of EDTA that we actually added to that solution. Okay? So to start off with, at the end point, we know the mole relationship between those two. Do we know the moles of calcium ion? We know its concentration, we don't know the moles. How can we get our concentration into moles? Convert. What else do we know about our calcium ion? Particularly the standard. What's your procedure tell you about it? Do you know anything else about that solution? What's that? I think you had it. No, not quite. It is a metal though. We have 10 milliliters of it. Was it really only 10?
Yeah.
Oh, okay. So we've got 10 milliliters. So why is that helpful? I can do a conversion where I can now convert the milliliters of calcium ion into grams of calcium ion. Okay, so we could start off our come on, pen. 10.0 milliliters of calcium ion. Our conversion, we've got 1 liter of calcium ion is 1 gram of calcium ion. Ooh, what's the problem here? We've got our volume set up where they could potentially interact and cancel, except the units aren't perfect, so what do we need to do? Convert. You'll notice that when I go through and show calculations, I will always show this, what some people typically ignore as far as a calculation, and that's because I have found I consistently goof the calculation. So I will always put it in there so I know exactly where the 1,000 goes. Okay? So my milliliters cancel out, my liters cancel out. I wanted moles. I've got grams right now. How can I get my grams into moles? I'll use the periodic table to do the conversion. Okay? One thing we need to tweak here real carefully because I think I've got this written wrong. It's 1 gram of what per 1 liter? Is it calcium ion? It's calcium carbonate. So when we do our conversion, we need to make sure that we aren't getting ion, but we're doing the calcium carbonate. Okay? So what we can now introduce is our molecular weight for the calcium carbonate. Anybody have that calculated or in their pre-lab? 100? 100 works for me. Okay. What's the relationship of calcium carbonate to EDTA? Do we have that relationship? Kind of, sort of. Does our balanced equation say calcium carbonate? No, it just says calcium ion. So technically what we would need to do is convert our moles of calcium carbonate into moles of calcium. How would we do that? What's the mole-to-mole ratio? 1 to 1. How do you know that? You look at, what was that? The balanced? Not the balanced equation, the balanced molecule. It's the formula that we're getting that 1 to 1 ratio of our mole of calcium and the mole of calcium carbonate. Sorry, I'm running out of space here at the end. Okay? Now I technically have the mole of calcium ion. What do I want to do now? I wanted to know how many moles of EDTA was added. How do I convert the moles of calcium to moles of EDTA? It's also a 1-to-1 ratio. Again, something that most people leave off, but I will include. 1 mole of calcium is 1 mole of EDTA. Great, what does that mean? We now have the moles of EDTA added. The whole goal of this was to do what, though? Standardize what? Calcium. No. Concentration. What are the units on concentration? Moles per liter. So far, what have we got? If we go through and track our units all the way through this, what do we have? We have moles of EDTA. How do we convert our moles of EDTA into concentration? What are the units on concentration? Really? Units, concentration? Big M, right? Which equals moles per liter. We've got moles. Where does that per liter come from? How did we get the EDTA added to the solution? Through the burette. So you added some volume from your experiment. Okay? Divided by the volume. I can't spell. It's fighting me all the way through. Volume added from burette. I think there's too many letters in that word, but okay. Cool, so what do we have? We have the concentration of EDTA from one trial. What happens if you screwed up that trial? Your standardization number is wrong. So what should you do to fix that? Do it again. What happens if both those trials are wrong? You'd have to do it again. So what we're going to try and do is minimize the experimental error by repeating the standardization attempt multiple times. Okay? At least 3 times. Okay? In theory, you should be checking your molarity or your molarity calculation at the end of each trial and verifying that it's pretty close to the other one. Okay? What should this number come out darn close to? Some of you are flipping back through. It's a good sign. 0.004 molar. That's what we were trying to make at the very beginning. Okay? This now tells us a much more accurate concentration of the EDTA solution. We're going to end up with, I think, 4 sig figs in this calculation. Not a big sig fig stickler, but don't remove too many in this experiment. Okay? Once we've got the concentration of EDTA solution nailed down, now we can go through and essentially run the exact same experiment, except now, instead of trying to determine the concentration of EDTA, oops, that should be EDTA, which I'm now then going to erase. Now we want the concentration or our hardness of our calcium concentration, which means we go through ultimately the exact same calculation, except now we don't know what our concentration of that is. What we do know is our concentration of EDTA being close to 0.04 molar. We'll know the volume added. We'll solve for the concentration of our metal ion. and we'll know the volume that we started of that. Okay. So we've got two volumes that we'll be measuring. We've got a volume of EDTA, which in all cases will be from the burette. How do you spell burette?
There's one R and one T.
I think it depends on which English you speak, Brit or American. Just make it up.
Whereas the other one has a pipette. And that one's volumetric, I believe. Okay? So now when we go through and do our calculations, ultimately we're going to get very similar, except now all of our units swap and we pretty much flip everything. We do the reciprocal of our calculations. Okay? What if we did that next titration incorrectly? Our answer would be wrong, so what do we do? Do it again. What if that one's wrong? Do it again. We'll try and average out all those results. So what you're going to end up doing is doing the sequence of titrations now at least 6 times. Okay? The rest of the calculations are ultimately just unit conversions. So when we go through and we did this calculation, except now for our calcium, what we would end up with at the end would be a concentration in moles of calcium per liter. So now we just erase all that. Yeah. What did we say that we actually wanted to figure out our water hardness? Way back at the beginning, back in our introduction. We wanted milligrams per liter. How do we do that conversion? What's the relationship between moles and grams? We've got the molar mass of calcium. Was it 40? Did I do that right? Is it 40?
Yeah.
Wow.
40.1 if you want to split up.
We got now grams per liter. We wanted milligrams. How do we do that? We now have milligrams per liter. Okay? We now have a value we could report and record that. Okay? Those are all the calculations that I actually remember. The rest of them are kind of meaningless calculations, which is why we'll just switch back to your handout. The handout goes through. You'll notice that the calculations are ultimately very, very, very similar to what I just showed, except instead of walking through it stepwise, like we went through and did, trying to do each of those individual conversions, they jammed it all into one big equation. Okay? In some cases, it's obvious what they're trying to do. In other cases, it's not. Okay? For instance, up at the top there, the value of this right here. Is that a unit or is that a number? That's a number that you got from the tall measuring device. That was the burette, in case you forgot. Okay? That would then allow you to go through and determine the molarity of your EDTA. They ask for a percent transmission, effectively a percent error. Okay? For a relative precision, that's where they want it in parts per thousand. They give you the calculation on how you go through and do that. It's not terribly difficult. So they give you all the individual stepwise on how to do that, so I don't walk through any of that. Okay? The very last thing, getting your parts per million. Okay? They again give you your calculation on how you go through and get that number. It's effectively the same thing as your milligrams per liter. So as soon as you get the milligrams per liter, you can now change your unit from milligrams per liter to just parts per million. And you've got the same thing. Okay? You'll notice again the calculation is very, very similar. They added a little bit more information here to help you figure it out. Okay? V here is going to stand for the volume from what? from your tall measuring device again, right? What's this big M? That's your standardized concentration. Put brackets around it for concentration. Okay? Questions about any of that? Okay. What do I expect to see in the resultant calculations? I expect to see all of these calculations as far as the results. So what kind of tables or data should you include with that? What do I want? I want this. So let's think about this. For your standardization, what are you going to record? Zoom in a little bit better so I get better handwriting here. We're going to have at least 3 experiments, or 3, let's make them trials, let's not call them experiments. Trial 1, trial 2, trial 3. What are you going to put in each of those 3 trials? Final what minus initial what? I don't know what that means.
So your standardization.
Okay.
volume delivered.
So we've got a volume of EDTA, okay, that you added from your burette. As far as what I want to see in your result is just the number. I don't want to see the final minus initial. I'll assume that you can figure that out. Okay? So just tell me the volume of EDTA that was added. What other pieces of information were necessary for that standardization?
The mass of your EDTA that you laid out.
I wouldn't include that here. I'd show that in your calculation. But the mass of the EDTA weighed out isn't different for each of these trials. You measured that out once to make your stock solution. Are there any other things that you measured? Volume of our calcium carbonate solution. Okay. As an added bonus for each of these, you should be including units. You can either include the units, like I am, super crammed up in there up at the top, or per each number, you can write it next to each number. Okay. The volume of calcium carbonate added, we should actually add an extra piece of information to that calcium carbonate. What should we add there? Concentration. Since we know the concentration in our standardization, we should specify that in our graph or our chart, our table. That's what it is. Okay? This ends up summarizing all of the results that you calculated or that you obtained in the course of your standardization experiment. Okay? You then use those 2 numbers to go through and calculate the molarity. So the next thing I would expect below this would be your calculation for the molarity of your EDTA. I only need 1 example calculation, and I do expect to see a general format as well as 1 sequence of numbers. Okay? So what we went through and solved for already was the general format, plug in some numbers, show that calculation as well. Okay? What else should follow from your standardization? Okay, we could show the average. Good call. I didn't think of that one. That's a really good one to use. What else? This is all the standardization. The parts per trillion. Okay, how precise were you? That should show up in your standardization section. What's that? The precision was parts per trillion. So that gets you through the calculations of half of your experiment. The other half of the experiment was now to the water hardness. You'll have, again, at least 3 trials. What things can you tell me about those 3 trials? know the volume of EDTA, you add it for each of those. Do you know the concentration of EDTA now at this point? Yes, that should show up in your table here, 0.004, roughly. And we know the volume of calcium ion that you started with. Okay. What are you going to follow all that up with? Now your calculations. For our water hardness. Okay. For each of those trials, and now also an average. Okay. In the process of calculating the molarity, just realize that we could add this for each of these tables. We could add the molarity of EDTA for this first one, so we know what the molarity is for each of those trials. And we could also, and I don't have the space to show it here, but we could also add an extra column for your water hardness value for each trial. That way all of your results are nice and succinctly organized. In theory, they look a whole heck of a lot better than what I've got scribbled up there. Okay? This should all get typed up. The calculations you may handwrite, but like I said, most, Word document things, software, will give you some kind of equation editor. Yes?
What does it say after EDT on the second chart?
I can't point to it quite right. Up here?
Yeah.
That's the concentration of your EDTA solution. So in this case, I'm going at what it's supposed to be relatively. If yours is way different, that's fine. Just report what it is. But you should report that because you know what it is, and so it should show up in the table. Is that a question? Oh. Other questions about it?
So this is all for the lab report, right?
This is all for the lab report. Yeah. As far as what shows up in your lab notebook, you'll probably want initial and final for all of your volumes from the burette, from the calcium carbonate. All of that is going to be volumetric pipettes. You don't need any initial final. You just measure it out from your pipette. It's 10 mils. I think it's 10 mils. Okay? Yes?
So you said for these reports that we only have certain parts repeated.
Yes.
So are those the only parts we have to do?
I was kind of waiting for someone to ask that. Yes, those are the only parts you have to do. So those are the only things I'll look at. If you want to do all the other parts, that's fine. But I'm not going to look at it unless you specifically ask me to look at it so that I can give you feedback. So for this report, introduction, results, and discussion. Results and calculations. Sorry. Okay. Questions about any of that? Okay. Since you guys have asked for me to record these lectures, in the future I will try and set up some PowerPoint slides to kind of organize it so we don't get this kind of grossness. Okay, so it looks a little bit easier to interpret. Any other questions? Okay.